So there was an intro video that kind of went over basic composition of blood. So if we looked at blood, there's blood in my tube, and if I spun it down, the majority of your blood are red blood cells. There you go. The other big portion of your blood is your plasma. And then there's this skinny little area in there that when you centrifuge it down, the heaviest red blood cells sink, where you find your white blood cells. And platelets. And that's where we're going to start talking today. The intro goes through a lot of the red blood cells, how we regulate red blood cells, what do red blood cells do. We're going to take a look at the white blood cells and the platelets today. So white blood cells make up less than 1%. So, imagine that even skinnier than there. Less than 1% of your actual blood itself means we have somewhere, and it's a big range, between about 4,800 and a little over 10,000 white blood cells per microliter. I was like, that's kind of a lot. Well, in relation to the other cells that are in there, like the red blood cells, it's not. Main function of white blood cells. Well, the main function of red blood cells is to do what? Not make it. The red blood cells. What do you think? I was going to say transport oxygen and some carbon dioxide as well. It's transport gases. White blood cells don't do that whatsoever. White blood cells' job is a lot of immune system function. So we have white blood cells that fight against a lot of different types of diseases. And although there's only one red blood cell, they all look alike. There are 5 different kinds of white blood cells. They each look a little different from each other. They each function a little different from each other. But they can move through tissue. They move when they call it an ameboid fashion. They kind of ooze. They kind of squeeze and ooze and get to wherever they need to go, pretty much wherever the infection is. If you ever have a white blood cell count over 11,000 per microliter, that's above the normal range, usually indicates that you have some type of infection. If you're fighting an immune system response, you're going to need more white blood cells. Your white blood cell count is going to go up. It again is why when someone comes into the doctor exhibiting whatever symptoms they have, and they don't really have any idea what's going on, they're just like, I feel really sick. Okay. And one of the first things they do is draw blood. There's a lot of things that your blood can tell you, and one of them is they'll look at white blood cell counts. If they see white blood cell counts up, they know there's an infection. And now depending on which of the 5 white blood cell counts that's highest or has increased the most, that can also narrow down, well, what kind of infection? From a bacteria, from some type of parasitic worm, from a virus? We can look at these white blood cell counts and look to see, a lot of what's going on in the body. Keep forgetting to click first. There we go. Now, of the 5 white blood cells, we group them into 2 groups. We have granulocytes and agranulocytes. Just means one has granules in their cytoplasm that pick up stain, and one doesn't have granules in the cytoplasm, so it doesn't pick up stain. What do you notice about all the names? There's 3 granulocytes. What do you notice about their names? They all have fills. I don't know. They're the fills. I don't know why. And neutrophils, eosinophils, and basophils are all granulocytes. And the agranulocytes just all have cytes in their name, the lymphocytes and the monocytes. Now, there's 5 of them. They do have a difference in abundance. And we separate them out, but just looking at percentages, the majority of your white blood cells are the neutrophils, then the lymphocytes, then the monocytes, the eosinophils, and then the basophils. So my little acronym for remembering the abundance of each of the white blood cells is never let monkeys eat bananas. You have the most neutrophils of the white blood cells. You have the least basophils of the white blood cells. And then again, we're going to be looking to see, do those counts change if there's an infection? Now, of the first granulocytes that we have, the first fill we have is the neutrophil. Identifying it, because we're going to get into blood next week, starting in lab a little bit. Blood. The neutrophils, looking at their nucleus. Usually a nucleus is round. Is this nucleus round? No. I always think it's the least neutral looking of any type of nucleus for the neutrophils. They usually have a lobed nucleus. It's usually multi-lobed, 3, 4, 5 little lobes in the nucleus. Now, these white blood cells are white blood cells that they become very active when there's a bacterial infection. They're called bacteria slayers. their job is to eat bacteria. So if you're suffering from a bacterial infection, they're phagocytic, you're going to have an increase, a huge increase in numbers of neutrophils. And again, when they look at someone's blood and they're like, wow, there's a huge increase in neutrophils. Wow, there's probably some type of bacterial infection happening somewhere in the body. Like they're attracted to the white blood cells. They can squeeze in between various tissues very well to try to get to where that infection is, but they want to eat bacteria. That's their main job, get rid of bacteria. Now, I was going to say, I forgot, Mike, they do also contain something known as defensins. These are antimicrobial proteins. So other than the fact they're going to eat bacteria, they themselves have proteins in it that try to reduce bacterial reproduction. So if there is an infection around and they're there to try to get rid of them, they can also inhibit their growth as they're trying to eat them. The eosinophils, their nucleus is bilobed, so it's kind of like two little balls in there. Their granules are lysosome-like. They're not exactly a lysosome, they're lysosome-like, which means they like to break apart and digest things. Eosinophils are found mostly when there's some type of allergy reaction. So if you're having some type of allergic reaction, asthma going to trigger the increase in eosinophils, but also if there's some type of parasitic worm infection. If you've got hookworms or pinworms or tapeworms or any other kind of worm, eosinophils' job is to coat those worms and destroy those worms. Now, so you see them a lot when people are having allergic reactions, and you see them a lot increase when there's some type of parasitic worm infection. Basophils, although it has a bilobed nucleus, you can't really see it. Basophils' granules are really dark. That all the cytoplasm has such dark staining granules that you don't even see the nucleus. There is a bilobed nucleus in there. No, you just don't really see it. Now, the basophil contains the granules in there that are in the cytoplasm contain histamine. Now, histamine is an inflammatory chemical that attracts other white blood cells to any type of infected site. We want white blood cells to go where there's an infection, whether it's a viral infection, bacterial infection, worm infection, whatever. We do want white blood cells to go to those infection sites, and this particular bacteria can, it has the histamine in there to try to attract white blood cells to those infection sites. Now, histamine is something that, yes, it's a vasodilator. It opens up your blood vessels so white blood cells can get where they need to go. And it also can cause issues if too much histamine is produced. When might you see too much histamine produced? Also in allergies. And if you have an allergic reaction to something, yes, eosinophils are going to kick in as well because they can also trigger making more histamine in the body. What do you take when you have some type of allergies? Antihistamine. It's, to kind of calm the histamine's action because it's that particular chemical. Although if you have an infection, we want white blood cells to go to that, but sometimes you have allergies to something that your body thinks is foreign, but really it's not bad for you. It's the pollen in the air is not going to kill you. And but our immune system thinks it is, and it's going to secrete all of this histamine. Now, the agranulocytes, the ones that have the sites in their names. The first one are the lymphocytes. Now, the lymphocytes are found in lymph nodes. It's partially where they get their name from. The highest concentrations are in the lymph nodes. In your lymphoid tissue, they are part of the lymphatic system, all these lymph things for a lymphocyte. These are the ones that are crucial to immunity. If you have immunity to something, these are the ones that can recognize foreign invaders and kill them, and then make memory cells later on in life so that you now have immunity to things. That's why we get vaccinated. Now, there are two types of lymphocytes. Now, looking at underneath the microscope, lymphocytes have a huge, massive nucleus, kind of thing, like you don't even see much cytoplasm. That one you see even less cytoplasm. It's such a massive nucleus. And although there are two types of lymphocytes underneath the microscope, they look the same. T lymphocytes are usually looking at intracellular pathogens. So viruses that are inside of cells, bacteria that are inside of cells, and T cells or T lymphocytes also can recognize tumor or cancerous cells and kill them. B cells, these are ones that will eventually give rise to what are called plasma cells that can churn out antibodies. And the antibodies will target whatever's in your body, a bacteria or whatever, will target it for destruction. And so I'm like, and with these, we can make memory cells. We have immunity, long-lasting immunity. And then the last type of white blood cell are the monocytes. Size-wise, of all the white blood cell size, they are the largest. Their nucleus, they say, looks more like a horseshoe-shaped or kidney bean-shaped. It's kind of just this long, curved kind of nucleus inside of there. And they are the largest white blood cells, but their biggest job is to eat. Just like neutrophil likes to eat a lot of things, they're big phagocytes. The main job of a monocyte is to turn into what's known as a macrophage. Based on its name, macrophage. Macro means big, phage means eat. These are big eating cells. That's what they want to do. They want to find bacteria, they want to find pathogens, they want to eat them and get rid of them. So they're actively phagocytic cells. They're just big eating cells. Now, there are also ones that can trigger your lymphocytes, those things, and I'm like to mount a full immune system response so that you can recognize things, you can get rid of them, and then have memory against them for the future. Now, there are some issues with white blood cells. We could have too few of white blood cells. It's known as leukopenia. Penia means lacking and leuko means white. So we're lacking or have a low white blood cell count. If you don't have enough white blood cells, you don't have a great immune system. You're not going to be able to recognize and get rid of things. Now, generally, low white blood cell counts are rare. And I'm like, it's usually some types of drugs, some types of cancer drugs that can lead to low white blood cell counts. Another type of condition with white blood cells are leukemia. This means you now have cancerous white blood cells. It will lead to an increase in white blood cells. Everyone's like, oh, that's good, extra white blood cells. The unfortunate part is, in leukemia, it's an overproduction of abnormal white blood cells. It means our cells are trying to reproduce so quickly, they don't do it accurately, and they don't make the white blood cells correctly, which means these white blood cells aren't going to do their job. So it's like, what's the point? Now you just have all these extra cells around that don't do anything because they were never made correctly. And so all of those cancerous white blood cells get into the red bone marrow and they take up room there. It can cause anemia because now you don't have red blood cells in there. We're not, if it's that red bone marrow is so jam-packed full of white blood cells, you can't churn out enough red blood cells and you can have anemia. It can cause internal bleeding in your bones. That it can actually cause death from internal hemorrhaging as well as overwhelming infections because you have no immune system response. Now, leukemia is an extremely dangerous cancer to have. Treatments, well, some type of radiation, some type of anti-leukemic drugs, and stem cell transplants if you can find a suitable match. And I'm like, but it's hard to treat. It's right there in the bone marrow, and you can't just remove it. There are some organs you can remove the cancerous sections. We need our bone marrow. That's where red blood cells are made. And I'm like, so you can't just remove that cancerous place. So you have to try to treat it and kill it without doing too much other damage to your other cells, including red blood cells. Now, one disease that likes to affect white blood cells is infectious mononucleosis, usually just called mono. How many have had mono? A few people. It's a common virus. It's a highly contagious viral disease. The official name of the virus is the Epstein-Barr virus, and it creates high numbers of atypical agranulocytes, which means you have large numbers of monocytes and large numbers of lymphocytes. Usually the lymphocytes is because it is a viral infection. Now, it's a virus that's affecting your immune system. It's a virus that's affecting your white blood cells. Symptoms, people that are mono, tired, achy, maybe a slight fever, chronic sore throat that doesn't seem to want to go away. Now, your immune system, luckily, if you're healthy, can handle it. And I'm like, however, it takes a long time. They usually say at least 4 to 6 weeks before you're really starting to feel better. And I'm like, there's, mostly they just say, go home, get a lot of rest, stay hydrated, and that's about it. And I'm like, but it's a virus that affects our immune system. Problem with this particular one, as it's affecting the white blood cells, you have a large number of white blood cells, and they all have to go somewhere to die. And they go to the spleen to die. And so what's going to happen to the spleen when you have a large number of white blood cells going there to die? It's going to get very large, and the spleen's on the side of the body. It's going to get very large. One of the big symptoms of mono is you have an enlarged spleen. And I'm like, it's sore, it's painful, it can get huge. Your normal spleen is maybe about this big. An enlarged spleen can easily get this big. And so they say a lot of times, well, not a lot of times, when you have mono, you shouldn't play any types of rough sports. Your spleen isn't really protected by your rib cage all that well, and especially if it's enlarged. And the problem with an enlarged spleen is you have an artery that goes to your spleen. If you bump something that's stretched way out beyond, what it should be, like a balloon that's stretched really, really big, and you bump it, what's going to happen to it? Yeah, it's going to pop. Thank you for the balloon sound. And I'm like, it's going to pop. Now, you have an artery that goes to it. What's going to happen if you rupture your spleen? You're going to bleed to death internally. You wouldn't even know. And I'm like, there's not a whole lot they can do. They're never going to get you into surgery soon enough. And I'm like, because they would say, don't play sports if you have mono. And I won't lie. I'm like, I used to teach high school, and all these students with mono, and I was like, whatever, play sports. Oh my God, you don't even know what could happen. You'd bleed out internally. No clue. There's a reason why they say, don't play sports when you have mono. It's that enlarged spleen, because all those white blood cells have to go somewhere, and you have a large number of them. Now, the other type of cell we're going to talk about that's also found in that little tiny space when we centrifuge our blood down, other than the white blood cells, are platelets. Platelets themselves are not cells. They're fragments of what was a really big cell. It's called a megakaryocyte because it was really big. Really big cell, megakaryocyte. It develops, but what eventually will happen to it is it will fragment apart. And so it was one big, huge, massive cell, and then it just fragments apart. Main job of platelets, they help in clotting. They're the big one, that if you get a cut in a blood vessel, we need these platelets to help form those clots. Now, we have platelets constantly circulating around in your blood. But we don't want them to just have a clot anywhere. I'm like, if you just have random clots anywhere that's just forming, you've got another whole big other issue if you have blood clots that are forming for no reason. So platelets, although they circulate around in your blood all the time, all day long, they are kept inactive. I'm like, they're not actually doing anything. They're circulating around, but something has to trigger them to stick to each other. And so nitric oxide, as well as hormones called prostacyclin, and I'm like, keep those platelets inactive, just floating around, just waiting for some type of damage to a blood vessel. Now, they're just a fragment of a cell, so they don't live very long either. And I'm like, once they fragment apart, they only live for about 10 days. That's it. Now, what keeps them around is a hormone called thrombopoietin. Poietin means making. Anything that has throm, because you're going to see a lot of thromb in some of these words. Anything that has throm in it means clot. And so this is just a hormone that's making the part of the cell that helps with clotting. That's where they get its name. It's like big words, but there's a reason why they're called certain things. Now, we want to stop bleeding. It's a process called hemostasis. Anything that has heme in the name means blood. Stasis means state. Pretty much we want to have a steady state of blood. We don't want blood loss, kind of the basic idea. It's a series of reactions to stop bleeding so that we maintain as close to the same blood volume as possible. It requires various types of clotting factors. We need platelets, and we need some type of injured tissue to start it all off. And it goes through 3 steps. If you get a damage to your blood vessel, 3 steps to stop you from bleeding out. Vascular spasm, I think these are my next 3 slides. Vascular spasm, platelet plug formation, and coagulation, the actual clot formation. The first step is vascular spasm. When we're talking vascular, we're talking about the blood vessel. In spasm, it's going to shorten or constrict on itself. So we have vasoconstriction of the damaged blood vessel. If you shrink your blood vessel, what's going to happen to the blood volume that flows through it? It's going to go down. That's the big idea. If you have a cut in your blood vessel, well, let's squeeze that blood vessel, and not as much blood is going to come out of it. And I'm like, it's the same reason why if you have a cut, what should you do to someone's wound? Put pressure on it. It's one of those, if the vascular spasm, while it's trying to do its own thing, if it's not working fast enough, you can help with the vascular spasm as well by putting that pressure on it. Our blood vessels know to constrict. So the triggers is if you have any injury to smooth muscle, because you have blood vessel innervating smooth muscle. If you have chemicals that are released by the endothelial cells that line the smooth muscle of your blood vessels. And platelets will also trigger that vascular spasm, as well as pain reflexes. If you're in pain, it's a lot of times because you have an injury, so you might already have that internal bleeding. Now, vascular spasm is most effective in smaller blood vessels. If you have a cut or damage to your arteries, is your artery going to be able to constrict enough for blood loss? And I'm like, it is most effective in the smaller blood vessels. That doesn't mean an artery won't try. An artery, if you have damage to it, will try to constrict, and hopefully it will slow it enough that you can hopefully get somewhere and get some medical attention. They say our arteries can constrict long enough that it can take 20 to 30 minutes for you to have complete blood loss. Hopefully that means you can get somewhere in 20 to 30 minutes to replace the blood. Maybe not. So I'm like, it's more effective in your smaller blood vessels than the large ones. Then after you've constricted the blood vessels, then you have to have the platelets action. Again, you have damage to a blood vessel. I know there's lots of stuff on here. And I'm like, here's the damage to the blood vessel. That's the smooth muscle lining of your blood vessels. This is the collagen fiber on your blood vessels. But you've got damage. You cut your blood vessel. So there's your damage. So you've got damaged endothelium. And I'm like, that exposed the collagen fibers. The platelets can't just stick to the inside of your blood vessels. That's a good thing. We don't want your platelets just to stick inside your blood vessels. They first have to be exposed to that collagen. Then they can stick. So it's only when you've had damage to the blood vessels and the platelets can stick to those collagen fibers that we start to form this clot. We haven't made it yet. We just start with what we call the platelet plug. Then, once they start to stick to these exposed collagen fibers, they will start to swell up. They'll start to secrete additional chemicals to attract more platelets. Got it on here somewhere. It's a positive feedback cycle. One platelet start to stick because there was damage. They secrete chemicals to attract more platelets to come to here. And the platelets will then start to stick to each other. Platelets themselves, again, don't normally stick to each other, and they don't normally stick to the inside of the blood vessel. They can only stick to the collagen fibers, and they can only start to stick to each other when there's been damage to the blood vessel lining. And so I've got it on there. They secrete chemical message, even including ADP and some other chemicals and hormones that allow them to all stick. That in itself is not a clot, because you just have platelets stuck to each other. It's not a very secure, long-term, plugged to, do anything with this. I'm like, it's just the starting. We're just trying to get platelets to cover some of that wound. And I'm like, once the platelets are there, then they actually have the clot forming. This is when we have fibers. The fibers are going to reinforce what the platelets started. That's when you have what's considered a clot. So it reinforces that platelet plug with fibrin threads. And it's because our blood has fibrous threads as well as cells that we consider it a living tissue. And I'm like, it's a liquid tissue, but it's a tissue. It also transforms some of your blood from a more liquid to a gel right around there. We want it sticky. But this is some of those fibrin threads. Here's some red blood cells stuck in those fibrin threads. There's going to be platelets stuck in there. It forms this big, huge, semi-permanent, goes away eventually, and I'm like, semi-permanent clot right on top of where that damage was. Now, there are a series of reactions that are needed to form these fibrin threads, and one particular vitamin. Vitamin K is needed for blood clotting. This is why people that can't clot blood very well need to have vitamin K injections. And I'm like, it's needed for blood clotting. Now, to form these fibrin threads, because we don't have these fibrin threads just hanging out, or we'd have clots where we don't want them, we need a bunch of hormones to eventually make the fibrin threads. We first have something called prothrombin, anything that has to do with clots. Pro is before, and I'm like, it's going to get converted into an enzyme called thrombin. We just remove the pro, and it becomes thrombin. It's a clotting enzyme. That clotting enzyme catalyzes another, or triggers another enzyme called fibrinogen. Gen means it's going to generate fibrin, and it becomes what's known as fibrin. It's that fibrin enzyme that makes the fibrin threads. So it's just this little series of different types of enzymes to ultimately make these fibrin threads. There's my little, step. First, the blood vessel is going to constrict. You've got the vascular spasm. Then you're going to form the platelet plug. You've got those little tiny kind of purplish platelets trying to cover that damage to the blood vessel. The platelets are going to secrete chemicals to attract more platelets. And then you've got that fibrous mesh anchoring it all together. And I'm like covering up wherever that damage was. There's an actual picture of some clots and like some of those fibrin threads. Now, although we've covered up that damage, there's still a gap in the blood vessel wall. You still cut it. And so what we can do is known as clot retraction. That clot squeezes in on itself to bring the two blood vessel sides together. So we've got that crack in that blood vessel, that cut. We're going to squeeze the clot to bring the whole thing together. It stabilizes the clot. Actin and myosin, those same things found in your muscle, are found in these clots. I'm like, we still find them in platelet cells. They're not as organized as it is in muscle, but we still find actin and myosin that can squeeze and pull the platelets together to try to pull those two blood vessel walls together. So it draws the blood vessel edges together, but then eventually your blood vessel will heal itself. It's made of smooth muscle. And we have to get rid of the clot. So it's a process known as fibrinolysis. It's just removing the clot after healing. After a couple days, when your blood vessel walls have healed themselves enough, we can get rid of all of the fibrin threads. The biggest is an enzyme called plasmin. It's a fibrin-digesting enzyme. It will break apart the clots. I was going to say, I know where I'm out of time. I'm going to go too far. I only have a couple more slides on that, but I'll talk about it. I'll record this video. I wasn't sure how far we get. I'm going to record the last little bit of this blood. Before I see you on Thursday, watch the remainder of this. It's just on blood, so it goes through clotting and blood typing. That's the last two things. The last part's about clotting and blood typing. And then before I see you on Thursday, you have an online quiz on blood. Otherwise, that's the only video you have to watch is whatever I didn't get through today. So watch the remaining part of blood, take the online quiz, and be ready to talk about the heart on Thursday.